Okay, we come now to the co-author of Mr. Grußtag, Mr. Kreppel. The title of his presentation is Multi-Parameter Average Strain Energy Density Criterion applied on the sharp material inclusion problem.
Okay, thank you. Thank you very nice for this introduction. So I will show similar approaches as my supervisor Jan Klusak, but this will be applied for another problem, which is the sharp material inclusion. So first I will very briefly introduce into the topic, then I will show how the stress is distributed near the sharp material inclusion, and this stress distribution is given by two necessary parameters, which are the stress series exponents together with eigenfunctions and generalized stress intensity factors. I will very briefly show how the generalized stress intensity factors can be calculated by means of our deterministic method in the case of a bimaterial junction, which is a model for sharp material inclusion. And then I will show how the multi-parameter strain energy density factor criterion can be applied on this problem, and this application will be shown on a numerical example where the stress reconstruction by pure finite element analysis will be compared to the analytical approaches. And in the final part of the presentation I will give a little talk about how our next steps will be, and I will conclude with conclusions. So motivation of our work is what my supervisor already said. We deal with general singular stress concentrators, which occur in particle or fiber reinforced composites. My talk is mainly about the sharp material inclusion with points of singular stress concentration where we expect the crack initiation. And our problems are these. We try to predict crack initiation direction and crack initiation load. The stress distribution near the sharp material inclusion is given by stress series, which is asymptotic series. This is the same series as you've seen in the previous presentation. However, this case is for complex valued factors. So the series consists of terms. Each term consists of generalized stress intensity factor. The parameter R, the distance from the concentrator tip to the power of exponent, and each exponent consists of eigenvalue. Depending on the value of the eigenvalue, we can have either singular terms or non-singular terms. The classical fracture mechanics uses mainly the singular terms, but in some cases the non-singular terms are needed, as I will show. The eigenvalues are dependent only on the local boundary conditions of the problem, which are the geometry and the material parameters, while the generalized stress intensity factors depend on the global loading and the global geometry. If we look at the distribution of calculated eigenvalues, which form the stress series exponents, we can see this distribution. This is the angle of inclusion opening, which means as we open the angle of the inclusion, we can see how the eigenvalues are distributed. So in the beginning there are two singular terms, while there is some angle near 90 degrees where the problem is characterized only by one singular term. And if we switch to the other side, if we flip to the other side to the problem of stiffer inclusion, there are again two singular terms, but similarly to the previous case, we can see that there is an angle where the problem will be characterized only by one singular term. If I can show you how to calculate the generalized stress intensity factors, there are basically two methods. Both methods use finite element analysis or assistance of finite element analysis. Our approach, the overdeterministic method, uses data, the stress data, stress nodal components in tangential, radial and shear direction, which are extracted on a circle near sharp material inclusion tip, and we can take as many values as we want. We can basically refine the mesh as we want. So we form a vector of these values on the right hand side. The left hand side is the matrix on the left hand side is formulated from the already known eigenfunctions and eigenvalues. And the vector here is formed by the unknown generalized stress intensity factors. You can see that there is a division between real and imaginary parts, so the complex valued stress intensity factors can be calculated. But the main principle behind this method is that we have much higher lines, a much higher number of equations than the unknowns. So no exact solution exists for this system of equations. So we have to minimize the residual vector and get the approximate solution by some means, for example by least square method. And we can extract as many factors as we want. There is a condition that we have to have more lines than the unknowns. So the principle behind the strain energy density factor criterion was already presented, so I won't go to the details. We search for extremal values which can be either global or local minimum. We can calculate these by this augmented equation, and to each extremal value and to the interface we can determine the generalized fracture toughness, which we will later compare to the factor, to the generalized stress intensity factor. And the condition for this bimaterial problem, the general condition, is that we look for the minimal value, and whatever minimal value is, there is the expected direction or material of crack initiation. My numerical example is this 3-buoyant bending specimen, which is made of aluminum matrix, and this notch is filled by PMMA inclusion. These are the geometric parameters of the problem and elastic coefficients. You can see that there are eigenvalues forming the stress exponents for 3 different geometrical configurations, 60, 90 and 120 degrees. In the first 2 cases we have 2 singular terms, while in the third case we have only 1 singular term. And let's look at the stress distribution near this problem. We are now looking at the stresses on a circle surrounding the tip of the inclusion in distance of 1 millimeter. For this case, where the inclusion is more compliant than matrix, and we compare the finite element analysis solution, the black squares, to the solution given by 1 singular term, 2 singular terms, or 2 singular terms and 1 non-singular term. And you can see that these 3 analytical solutions overlap here, and they are quite close to the actual solution which is given by finite element analysis. But if we add the 4th term, the second non-singular term, we can increase the precision of the solution so it perfectly matches the finite element analysis solution. I didn't say that, but we have 3 different components of stress distribution: the radial, shear and the tangential stress distribution. Here I show how we calculated the strain energy density factor for this problem. And similar to the bimaterial notch problem, we can compare the singular term solution of SEDF to the singular and non-singular term solution of the SEDF. And when we can see that there are two minimums, one corresponding to the matrix and one corresponding to the inclusion. But we also have to investigate the generalized fracture toughness on the interface. And then we compare the values which are given by singular terms and values which are given to the non-singular terms. And you can see that the difference there is in units of percents, but the smallest value of the generalized fracture toughness corresponds to the interface. So we expect the failure to occur to the interface. Similar situation is analyzed here, where we have stiffer inclusion in a more compliant matrix. So we actually switched the materials. The eigenvalues are here. So in three configurations of 60, 90, and 120 degrees, we have two singular terms. The geometry is the same as the problem earlier. But if we look at the stress distribution, you can see that by using two singular terms, the solution is actually quite far from the solution given by finite element analysis, and we can increase the precision of the stress distribution dramatically by adding first non-singular term. And you can note that this stress distribution is on a distance which is 10 times closer to the previous case. It's on a 0.1 millimeter, which means that it should be more precise. So what do we do about it? Well, there are actually 8 cases how the sharp inclusion problem can be loaded, and these cases show different behavior in means of description either by only singular terms or singular and non-singular terms. On the left-hand side are the cases where the inclusion is more compliant than matrix, and on the right-hand side are the cases where inclusion is stiffer than matrix. And from our calculations, we conclude that these two cases, together with these two cases, are described well by singular terms, while these cases are, we need to employ also non-singular terms to describe the stress well. So these are our next steps to conduct a systematic study to study this phenomena, to see in which situations we need to employ also non-singular terms. So, to conclude, I've showed how the stress is distributed near the sharp material inclusion tip. I've showed that for the inclusion problem, where the inclusion is more compliant than matrix, the singular terms are sufficient, but in the case of stiffer sharp material inclusion loaded as I showed, there can be critical addition of precision by adding the non-singular terms. For the case for the application of strain energy density factor criterion, we have difference in units of percent with maximum of 7.7% increase. Thank you very much for your attention.